Let's start the second week of the convex geometry. So the goal is to define dimension of convex sets here. Maximal affine independent subsets are fundamental to define the dimension of affine subspaces. A similar scenario to the case in linear algebra. Here is the really objective of this chapter. We want to define the dimension of convex sets, and first we need dimension of affine subspaces. And we are going to use all we have from linear algebra. So there are a parallel between linear algebra and affine algebra. So let's see. Here definition 9. An affinely independent subset T of an affine subspace K or Rn is called maximal if there is no affinely independent subset T prime different from T of K such that T prime includes T. Let's go to a couple of examples. Here example 1. There are 3 affinely independent points that form a maximal set in R2 but not in R3 or any Euclidean space with dimension greater than this. Here now example 2. There are 4 affinely independent points that form a maximal set in R3 but of course not maximal in any n space for n greater than or equal 4. The next proposition guarantees the existence of such maximal set such that the cardinality of this maximal set is less than n plus 1. This is a conclusion of the fact that we know from linear algebra. See, we know already that the dimension of Rn is n in linear algebra. So we are going to use these facts here to define the dimension in the affine algebra. Here is proposition 4. A set x0, x1, xr, the subset of Rn, is affinely independent if the set of vectors x1 minus x0 dot xr minus x0 is linearly independent. Moreover, x0, x1, xr is a maximal affinely independent set in Rn if and only if x1 minus x0, x2 minus x0, xr minus x0 is maximal linear independent set in Rn. And then of course R must be equal to n. Again, the reason that R must be equal to n is conclusion that we know the dimension of Rn is n in linear algebra. This is the linear dimension, and this is a fundamental proposition that really transfers all the information that we have from linear case to the affine algebra. Here is a simple example for R equal to 2. No? We have 2 vectors that are linearly independent as the basis for the 2 plane and correspond to the 3 points that are affinely independent in the 2-dimensional affine space. This is a remark. Proposition 4 shows that the elements of affine algebra are quite similar to that of linear one. Existence of maximal affinely independent subset in arbitrary affine subspace and also is consequence of proposition 4. Again, here is talking about the same parallelism that I mentioned. Here there is an important catch in this definition. When we want to define the definition of basis, we are going to talk about this very critical point later. Here is that critical point really. In fact, to define basis and dimension for affine subspaces, we may rewrite proposition 4 for an arbitrary affine subspace of Rn. Okay, let's see what it means. But here, instead of proposition 4, we decided to choose proposition 5 to define the definition of the basis really. Okay, let me explain you a little bit about the proposition 4. What does it mean? We want to define the basis, and the basis is just the cardinality of the dimension is just cardinality of a basis. Okay, if this definition will be well defined if all these bases have the same cardinality, and proposition 4 exactly explains this, because we already know that this definition is well defined in the linear case, so will be similar things for affine algebra. But now proposition 5 also does this directly, so the definition of the basis and dimension will be well defined. Okay, let's go to proposition 5. This is the definition of basis. A maximal affinely independent subset S of an affine subspace K over N is called an affine basis of K. Okay, then consequently K is equal to affine whole of S, and X in K can be written uniquely as an affine combination of the elements of S. Remember, here there are 2 points in this relation. First, the maximality of this set S implies that K must be half S, and since this basis they are affinely independent, then that presentation must be unique. So there are two things: uniquely and maximality implies that is the real generator of the whole affine subspace. There is a note here: the existence of the maximal affinely independent subset of K is a consequence of proposition 4. Remember that we know that the definition of the dimension is well defined in the linear case. All the bases have the same cardinality, and the maximal set exists over there. We know that because the dimension of every subspace is less than or equal to n. So this definition also well defined in the affine case, and this maximal affinely independent subsets exist in the affine case. So here we go to proposition 5. For any affine subspace K over N, there is a unique linear subspace L such that K is equal to L plus x0. For some x0 in K, here is one example. We have a linear subspace, we have an affine subspace K. For this K, there exists a linear subspace L that's parallel to K. Both of them are lines in this case, such that K is equal to L plus x0. In fact, this means that for any x in K, there exists some x1 in L such that we can write x equal to x1 plus x0. Now from these two propositions 4 and 5, we can come to this conclusion. Suppose x0, x1, xr is a subset of K, the affine subspace. We define L equal to span of x1 minus x0, x2 minus x0, xr minus x0, and then define K is equal to L plus x0. Then the set x0, xr is an affine basis for K if and only if x1 minus x0 to xr minus x0 is a linear basis for L. This is really the crucial result, the summary of those propositions. This is what enables us that always, whatever result in affine algebra we want to prove, really, we use this proposition to go back to the linear case, and we use the result of the linear algebra here to prove something for the affine case. Here comes to the objective, that to define the dimension of the subspaces and then convex set. The dimension of the unique linear subspace L corresponding to the affine subspace K will be called the dimension of K, denoted by dmeg K. This is the one that really we need to be well defined, and now of course L is unique, is a well-defined dimension, so dimension of K is well-defined. So this is result of proposition 5. Remember, we could define this using proposition 4 now, but this is another approach to define the dimension of this affine subspace. So let's go to next step. We also define dimension of empty set equal to -1 for convenience, and of course dimension of a single point is 0, is a consequence of proposition 5. All different affine bases of an affine subspace have the same cardinality. This is also a conclusion of proposition 4, and also we can derive from both now definitions, as it is case for the linear subspaces. As a matter of fact, those bases could be used to define the dimension as well. This is what we explained several times until now. Okay, here is the proposition 6, that is a consequence of the proposition and basically 4. Any affine basis of k-dimensional affine subspace K has k plus 1 elements, and for any affine independent subset S of affine subspace K, there exists an affine basis of K containing S. This is just a result of the definitions of, and again applying this proposition 4. So these are the classical results, again coming from linear algebra to affine algebra. In any n-dimensional space Rn, a line is one-dimensional affine subspace. This is the definition. Okay, here is a formal definition of hyperplane. Hyperplane in Rn is an n-1 dimensional affine subspace. Hyperplane in R2 are lines, but in R3 they are usual two-dimensional planes. Let's go to two examples. Here, example 1, a line is a one-dimensional affine or hyperplane R2. In example 2, shows a regular plane, which is a hyperplane in R3. Here's the definition, the main definition of this section. For a convex set S in Rn, the dimension of S denoted by dm S is defined to be dm f S. So we just compute the affine whole of S, and that is the dimension that will be the dimension of S. For example, a line segment L dimension is 1. The dimension of circular disk is 2. But for a solid ball S in Rn, dimension is n. Let's go to examples. Here is example 1. We have a one-dimensional convex sets, closed convex set. These are closed segments in a line. In example 2, we have a two-dimensional closed convex sets, which is the affine whole is the plane here, a two-dimensional plane. Again, in example 3, we have a two-dimensional, but here is open convex sets. In both example 2 and 3, you see that the affine whole of S is a plane, a regular plane. So this is the theorem 3. For affine subspaces K1 and K2 of Rn with intersection non-empty, we have dimension of K1 intersection K2 is greater than or equal dimension of K1 plus dimension of K2 minus n. The proof of this theorem is very straightforward. It's directly use of the similar theorems from linear algebra. So just you can, for example, you can just translate any points of the intersection of K1 and K2 to the origin and then apply exactly the corresponding theorem in the linear case. Let's go to example that we have here. K1 is a line, dimension 1. K2 also is a line, dimension 1. The intersection K1 and K2 is a point that has dimension 0. So dimension of the left hand side is 0. The right hand side, K1 is 1, K2 is 2, minus n, we are in the plane, so the right hand side also is 0. So the theorem satisfies in this case. Of course, if n is greater than 2, 3 or higher, the left hand side has still the value 0, but the right hand side will be 2 minus something bigger than or equal to 3, which will be negative. So always theorem satisfies. Here this is a very important special case of part A. Let K be a non-empty affine subspace of Rn and H a hyperplane not containing it, such that intersection is not empty. Then dimension of the intersection is dimension of K minus 1. Remember that the intersection also is affine subspace. So it just explains the dimension of the intersection that will be very, very useful in the applications. We are going to have a proposition that is really bridge from convex geometry to formulations for linear program problems. We'll see how. Proposition 7. Every hyperplane H over Rn can be written as a solution set of some linear equation Cx equal to alpha, where C and X are vectors in Rn and alpha is a real number. So let's say H is a given now hyperplane that is presented by all x in Rn such as Cx equal to alpha. Then the Euclidean space Rn can be partitioned into two closed half spaces that we denote them as H minus and H plus. The H minus is all those x that Cx is less than or equal to alpha, and H plus all those x that Cx is greater than or equal to alpha. These are closed subsets of the n-dimensional space and are a very essential tool in definition that comes later for the geometry of linear programming. Note that the symbols plus and minus here can be exchanged very easily because they depend only on the representation of H that can be written also as, for example, H equal to all of the x, such that minus Cx equal to minus alpha. However, if H minus and H plus are closed convex sets, and always we can write H is equal to H minus intersecting with H plus. So only H doesn't define really this H plus and H minus uniquely, but if presentation Cx equal to alpha is given and fixed, then of course H plus and H minus are unique.